All right, so what is non-equilibrium? And in this situation, we're talking about mechanical stuff like things moving and forces and stuff like that. Well, the short answer is it's when an object has a non-zero total force acting on it, or it's got a force on it that isn't zero. So remember, you may have already looked at the tutorial about equilibrium. When an object has no total force acting on it, it's said to be in an equilibrium situation. And when an object does have a total force acting on it, it's said to be a non-equilibrium situation, or the object is in non-equilibrium. Well, that's lovely, wonderful, but why do we care? And again, by paying attention to equilibrium or non-equilibrium, we can tell a whole lot about how an object will move, whether or not it's an electron, a logging truck, the space shuttle, a part you're designing in an engine, or molecules moving through cell membranes. If you can know about forces, you can figure out things about how they'll move, and it's really useful in a lot of different situations. Hey, we'll look at more about how and why things move the way they do because of the forces they do or do not feel when we learn about Newton's laws. So we're not going to get too far into that with this. We just want to make sure we know what non-equilibrium is. Another reason to care about it is if we already know something about how the object is moving, we can also know then something about the forces that are acting on it. So it kind of goes both ways. If we know about the forces, we can say something about its motion. If we know its motion, we know something about the forces. So it's like being a detective. It lets you figure things out. All right, so let's get right to some examples. Let's see here. How about if we have any old object like, let's see. How about we have a rabbit. There's a rabbit that you have dropped from an airplane. Don't worry, it'll be okay. If you drop it from the airplane and it's falling through the sky, it's likely to have the force of gravity acting on it. So the force of gravity acting on this rabbit is actually the same thing as the weight of the rabbit. And maybe this rabbit weighs, let's say 25 newtons. So if the rabbit has just started falling, there's probably not much air resistance pushing back up the other way yet, and we'll ignore it for now. But maybe we most certainly have gravity acting. So in this case, the only force acting is gravity, and there's nothing to balance that out. So we know we're not going to be in an equilibrium situation. There is a non-zero total force here. F total, in this case, will be 25 newtons down. That one's pretty easy. There's only seems to be one force acting, so that's the total force also. If we're a little more realistic with the poor rabbit as it's falling out of the airplane, then we'll realize that air resistance will actually play a role as well. If you don't believe this, stick your face out of the window as you're driving down the highway, hopefully not while you're driving, maybe when you're a passenger, at 65 miles an hour, and you'll feel a lot of force on your face. And that's because of the air resistance. Most people have also stuck their hands out the windows and made them wave up and down, and it feels kind of neat. If you haven't done that, try it. So we have our little rabbit again, our little stunt rabbit. Here it is. Whiskers and all, little feet, little bunny paws. Okay, but this time, if we have the same rabbit, then we expect it to be the same weight and have the same force of gravity acting on it as before. So I draw the tail of the vector on the rabbit. We'll call the weight, or the force of gravity, 25 newtons like before. But this time, let's say more realistically that there is some air resistance. So we're going to draw a force up due to air resistance. If any of you guys have heard about terminal velocity, it starts to be related to the stuff we're talking about right now, but I won't get into that right now. Let's say the air resistance is 10 newtons. In this case, what's the total force acting on it? Not 35. It's tempting to add the 25 and the 10, but we do realize they're in opposite directions. If you were pulling on something in one direction and you had a friend pulling on another direction, in the opposite direction, you wouldn't really expect those forces to add up like that. In this case, since they're completely opposite each other, we can subtract the little one from the big one and know the total force is going to be in the direction of the bigger one. So in this case, F total, because the two vectors we're considering are completely in the same in the same line with each other, the math is pretty easy. We can just say it's going to be 25 minus 10, or 15 newtons. And since it's a vector, we can't really just give a number. We should also indicate the direction, and it's down. So the rabbit in this case is still feeling a force pulling it down, but not as much as before. Good. Let's look at another example. Whoops, wrong way. What happens if we've got a little bit of a different situation where you've got, let's see here, we could have, let's see. We could have a peanut butter and jelly sandwich. I don't know, it seemed like the good idea at the time. Pretend that's a peanut butter and jelly sandwich. There, bread, 3 dimensions, everything. And if it's really stale so it doesn't fall apart and we all yank on it in different directions, we could have my force acting in this direction, and maybe that's 10 newtons. Not tugging that hard. And maybe you're pulling in this direction, with 8 newtons of force. And maybe some guy named Earl is pulling in this direction with, let's see, how about, that looks like it's about another 8 newtons of force. Thanks, Earl. So in this case, all the vectors aren't completely in the same line, so we got to be a little more careful. There's actually a number of ways to deal with a situation like this, especially if we knew exactly what this angle was. There's a number of ways to add vectors in this situation. And when you do that, you have options. And we're not going to hit all those options here or try to explain the details. But one way is to add the vectors graphically. You actually use the pictures of the vectors to help you figure out the total force. Another one is to use trigonometry. And many of you guys may not have used or learned much about that yet, but you will eventually. And look at what's called the components of a vector. How much does a vector point in the x direction? How much does it point in a y direction? And how do we deal? And we can deal with it that way in a pretty effective way. So we can add by components. but you usually need some trig to be able to do that effectively. And there's another way, at least another way, using something called the law of cosines, which can sometimes be really handy, and sometimes it doesn't give us all the information we want. Whoops. Cosines. But what I'll do right now is give you a really quick version, just because it kind of makes sense, is how to do this graphically. If I take the tail of one vector and put it on the head of another vector and keep the vector pointed the way it originally was, I can kind of add up the vectors. So for example, let me see if I can do this here. If I take the vector from u and I move it over and I put its tail, which is the end that's not the arrow, on the head of my vector, I get that for a result. And then if I take Earl's vector, hopefully, oh boy, Earl's going to give me a hard time. I take Earl's vector and I move it down here. Wait, you know what I'm going to do? Earl. Let's see if I can let's see, grouping, ungroup. Ooh, my goodness. And I'm going to ungroup this guy back again here. That'll be a little better. And if I take Earl's vector and I put the tail of his vector on the head of yours, I get that. And what happens is we can say, okay, my force does a lot of pushing to the right, your force does a lot of pushing down, Earl's does some pushing back to the upper left, and the total force is actually, if you went directly from the peanut butter and jelly sandwich right to the end of Earl's vector, we would get a total force, F total is the blue one. And there are ways to do this to actually get the actual angle and get the number, but that's not our point today. Good. So 3 examples. Only one force acting, so that's the total force. Example number 2, we've got 2 forces acting, and they happen to be in line, opposite in this case, so they subtract from each other. So that math there is pretty easy. Gets a little more complicated, but the idea is kind of makes sense if you've got vectors that are pointing in weird directions. But you can at least add them graphically to get a sense of what's going on until you learn some other ways to do it. Thanks.